We are going to start now the first chapter of class 11th mathematics, sets. So we start this chapter with the definition of a set. So set is a well-defined collection of objects. So there are two terms over here. One is this term objects, and second term we have over here, it is well-defined. So object means anything in this universe, whether it is living or non-living, it is called an object. And when we are talking about this term well-defined, we explain this term with an example. Suppose we are saying we have to write the collection of all odd numbers less than 10. Then we start listing these numbers. The first odd number less than 10, it is 1. The next number is 3. Next we have is 5, 7 and 9. So this is the collection of all odd natural numbers less than 10. We are saying this collection is a fixed collection. Whosoever will write this collection is fixed. The elements in this collection, element means we are saying these objects. These are also called the members, elements or points of this collection. So these elements over here, these are fixed. These are not going to change. But when we are talking about, suppose the next example is given over here. When we are talking about the collection of difficult chapters of a book. Suppose someone asks me that what are the difficult chapters of this book, and I list them. Say I am saying it is chapter 1, chapter 7. These are the difficult chapters. Suppose someone asks another person that which of the chapters of this book these are difficult chapters. Then he may say that suppose it is chapter say 3 and chapter 9. These are the difficult chapters. So difficult, when we are talking about difficult chapters, the definition of this difficult, it may vary from person to person. So there is no fixed definition. This term is not well defined. That what is the meaning of difficult chapter over here. So this is how we differentiate between the well defined and not well defined objects. More examples are given on our next slide. So we come back to our definition over here. So our definition of the set is a well defined collection of objects is called a set. And the notation used for set to represent a set is the capital letters they are used. These are mentioned over here. We may write a set as, suppose I am talking about this is a set. We may write it as A is equal to this. So this is a set because it is a well defined collection of objects. Next we give some examples of some well defined and not well defined objects. So first example we have is the collection of all vowels in English alphabet. So this is a well defined collection. We are saying well defined elements are there or well defined objects are there. And if we have to list all these elements, we are writing it is A, E, I, O and U. Why we are putting these brackets? We generally keep the elements of the set in these kind of brackets. These will be explained in our next slides. Next, second, we are talking about collection of all odd natural numbers. This we have already seen. Next, we are saying the collection of all prime numbers less than 20. If we have to list all prime numbers less than 20, then these are 2, 3, 5, 7, 11, 13, 17, 19. So these are the prime numbers less than 20. One is not a prime. One thing you should keep in mind when we are talking about prime numbers, we are saying one is neither a prime number nor a composite number. This thing is clear to us. So this collection, it is well defined that we cannot add any element to this collection. We cannot remove any element from this collection. Next we have is all possible roots of quadratic equation. This quadratic equation is given to us. Then we are saying that the collection of all possible roots, if we solve this equation, if we find the roots, you will get the answer is 2 and 3. So we are saying that all possible roots of this quadratic equation, it is minus 2 and 3, and this collection we are writing it is minus 2 and 3. So we are saying this is a well defined collection. These elements, these are fixed. Next we have given some example of not well defined. So first is the collection of 5 most talented. This word talented over here, it has no definition. When we are saying talented writers of India, this word talented has no definition, fixed definition. For me, the list of most talented writers may be different. For someone else, it may be different. Next is the collection of most dangerous animals in the world. This word dangerous, it is not well defined. Next we are saying the collection of 5 most renowned mathematics. So if we list all these elements or all these objects, then it may vary from person to person. These are not fixed. So that is why we are saying these are not well defined collection. These are not well defined collections. Similar examples are given over here. If we are talking about rich persons, if we are talking about honest persons, honesty has no definition. If we are talking about good players, if we are talking about old people, suppose I am taking the case of old people, for me, I might be saying that the person whose age is greater than 60 years is old. Someone else may consider, no, the person whose age is greater than 70 years is old. So there is no fixed definition for this term old, that what we should consider, to whom we should consider that he or she is old. Similarly, if the term we are using it is short boys, this term short has no definition. Next is difficult chapters, this term difficult has no definition. So all these collections, they do not form a set because these are not well defined collections. Next we have is notation of belongs to. So if we are writing any set A is there, we are saying any set A is there, it may be of numbers, it may be of people, it is a well defined collection of objects. And if we consider any element from this set A, then we write A belongs to A. It means, what this thing means is that A is an element of the set A. This notation is for belongs to. We read it like A belongs to capital A. This small letter, small a, this small letter, it means it is the element we are representing. With capital letter, we are representing the set. So we are saying this is an element of A, we are saying it belongs to A. Now, if an element is not present in A, then we say, suppose I am writing over here that there is an element B, which is not an element of A, which does not belong to A, then we write A does not belong to B. So this is the notation for does not belong to. So we explain this with this example. We are saying A be the set of all even whole numbers less than 10. So even whole numbers less than 10 means we are talking about whole numbers. Whole number starts from 0. So we are saying it is 0. Then we are talking about even numbers. It is 2, 4, 6, 8. This term is important over here that we are talking about less than 10. So 10 is less than, equal to if it is, then 10 will be there, but it is less than, so it is up to 8. Now if we look at this collection, then this element 0 is there in this. We are writing this collection as, this set as A is equal to this. We are saying this element 0 is there, so we write 0 belongs to A. If we look at this element 10, so 10 is not there in this list, 10 is not the element of this set, so we are saying 10 does not belong to A. Then 3, it does not belong to A. Then 6 is there in this list, so we are saying 6 belongs to A. So we are saying if this complete element is there in the set, then we say that element, it belongs to that set. Now next we have method to describe or specify a set. So there are two methods. The first method we have, it is the roster form or the tabulation method. So in this method, we list all the members of the set within braces and separate them by commas. So first example, we have all factors of 24. So we list all the elements over here. So the first factor we have, it is 1, next is 2, next is 3, next is 4, next is 6, next 8, next 12, and next 24. Next is all integers between -3/2 and 11/2. So if we look at these numbers, -3/2 and 11/2. So -3/2 means we are talking about -1.5. If we draw the number line over here, it is 0 over here, it is -1, -2, then it is 1, 2, so on up to, we are saying it is 5, and then it is 6. This number, it is 5.5. So where these numbers are lying, this number is -1.5 is over here, and this 5.5 is over here. So we are saying, but the integers we are talking about, it is -1, 0, 1, 2, 3, 4, and 5. So this is the collection we are talking about. It is all integers between -3/2 to 11/2. Next is all consonants preceding k. So if we start listing the elements, the first we have, it is A. We are saying A is not a consonant, it is a vowel, so it is not the element of this set. Next we are talking about B, C, D, E, F, G, H, I. These are the alphabets preceding K. Out of these alphabets, A, E, and I, these are the vowels. So consonants we have, it is B, C, D, F, G, H. Next we have is the letters of the word trigonometry. So if we have to list all these letters, we are going to write, suppose all the letters, we are saying it is T, R, I, G, O, N, O, M, E, T, R, Y. These are all the letters we are writing. But it is important to note over here that the repeated letters we write only once. When we are writing the collection, the repetition is not allowed. So we are saying this O is repeated twice, so we remove this O. Suppose this T is we can remove this T from here because it is repeated. Suppose we are removing this R from here. Next we are talking about the letter I, it is once, G, then N, M, E, T, R, Y. So the collection we obtain, it is I, G, N, O, M, E, T, R, Y. So this is the collection we obtain. It is important to note over here that the collection we have mentioned over here, it is this. But both these collections, these are same because the order in which the elements are listed is immaterial. We are saying I is over here, I is over here. Then we have G, this is the element G. Then we have O, this is the element O. Then we have N, this is the element N. Then we have M, this is the element M. We have E, E, T, T, R, R, Y, and Y. So we are saying both these sets, they are same. So these two things, these are mentioned over here, that repeated letters are taken once each, and second is the order in which the elements are listed is immaterial. Both these sets, they represent the same, both these collections, they represent the same set. Next is the months having 30 days. We are talking about the collection, the months having 30 days. So which months have 30 days? It is April, June, September, and November. So these are the months having the 30 days. So this kind of method in which we are listing all the elements, it is called the roster form or the tabulation method. So what is important to note over here? First thing we have seen that the elements should be written in braces. We put the comma to separate those elements. Next thing we have seen from this is that the repetition is not allowed. It means that repeated letters, they can be taken only once. And last thing we have noted over here is that the order in which the elements are written in this list, in this collection, it is immaterial. Now the second form to represent the set, it is the set builder form. Now in this method, we list the property or the property satisfied by all the elements of the set, and we write it in the form, put the bracket over here, we write x, this is the symbol for such that, and then we write x has properties p. It will be more clear to you that with the example. Suppose we are talking about this first case, we are talking about the set A. It is 1, 2, 3, 4, 5, 6, 7. This is the collection given to us, and this is given in the roster form. So we can write this as, we are saying A is equal to x. X means what are the elements of A? These are x. And what are x? First thing is, all the x, they are natural numbers, and x is less than 8. You can also write it as x such that x belongs to n and x is less than equal to 7. So it is up to you that how you want to write. So how we read this is, we are saying A has elements x, and what are x? Definition of x is a natural number and x is less than 8. So if this is the set builder form, and if we write the collection, the complete collection over here, then it is the tabulated form. In the second example, we have the set B. It is 1, 2, 4, 7, 14, 28. So these are basically the factors of 28. So we can write this collection B as, B is equal to, B has elements x, and x is a natural number. First thing, x is a natural number, and x is a factor of 28. So we are saying, we are talking about the collection of all natural numbers which are factors of 28. Next we have the set C. It is 2, 4, 8, 16, 32. So these elements, these are basically the powers of 2. So how we are going to write this collection? We are saying it is x. We are talking about the set C. It is x such that, first thing is, x is equal to 2 raised to the power n. What is n? N lies between 1 and 5, and 1 is less than equal to, n is less than equal to 5, and n is a natural number. So this complete collection will become, if we have to write the elements, if how we are going to read this, we are reading C is equal to the set x such that x is equal to 2 raised to the power n. Now we require this definition of n. N, these are numbers from 1, 2, 3, 4, 5, and n belongs to natural numbers. N is natural number between 1 and from 1 to 5. So if we have to list the elements, we are saying we will put n is equal to 1, the answer we get it is 2. The value of x we get it is 2. If we put n is equal to 2, the value of x we get it is 2 raised to power 2, that is equal to 4. So likewise we can list all the elements of this set. Next question we have, it is d is equal to minus 6, minus 4, minus 2, 0, 2, 4, 6. So these are multiples of 2. So how we are going to write this collection? It is the set D is equal to, these are the elements x we are saying, if we have to list them. So these are of the form 2n. N is varying from minus 3 is less than n is less than equal to 3, and n belongs to Z. Z means collection of the integers. So we are saying n is an integer from -3 to 3. What this thing means? N is an integer from minus between these elements. It is -3. N can have values -3, -2, -1, 0, 1, 2 and 3. If we substitute these values of n over here, the values of x we will obtain. On substituting -3, we will get -6. On substituting -2, you will get -4. So on substituting these values, you will get this collection D over here. It is -6, -4, -2, 0, 2, 4 and 6. Next we have is the set E over here. The elements of this set, it is 1 by 2, 2 by 3, 3 by 4, 4 by 5, 5 by 6, 6 by 7, 7 by 8, 8 by 9. So how these elements are being formed? We can see the pattern over here, that this first element is 1, then it is 1 plus 1, 2. The next element it is 2, next it is 3. So the numerator is 1 less than the denominator, or we are saying denominator is 1 more than the numerator. The first element is starting from 1. So how we are going to write this collection is, we are writing it is the set E is equal to x such that, first thing is the first element we have, it is 1. So we are writing x is equal to n over n plus 1. It is clear from here that numerator is 1 less than the denominator. What is n? N is a natural number. It is 1, 2, 3, 4, 5, 6, 7, 8, 9. And the first value of x we have, it is 1 by 2. So n is starting from 1 and going up to the last denominator part over here. We have it is n plus 1 is equal to 9. So n should be equal to 8. So we are saying the n is varying up to 8. So we get x is equal to n by n plus 1, where n is a natural number and n varying from 1 to 8. The next collection we have, it is 1 by 2. The next elements we are talking about, these are 1 by 2, 2 by 5, 3 by 10, 4 by 17, 5 by 26, 6 by 37 and 7 by 50. So how we can write this collection? We are saying it is x such that x is equal to, now what is the pattern over here? If we put this element as n, then the denominator part is n square plus 1, where n is a natural number and the values of n, they are varying from 1 to 7. You can look at this pattern over here. If suppose I put n is equal to 6, if the values of n we have 1 to 7, so if we put n is equal to 6, the answer we will get x is equal to 6 over 6 square plus 1, that is equal to 6 by 37, and it is an element in this set over here. If we put n is equal to 7, we will have x is equal to 7 over 50. This is the element over here. Now the next we have, it is this set G. It is the elements, they are 53, 59, 61, 67, 71, 73 and 79. So these are basically the prime numbers between 50 and 80. So we can write this set as G is equal to x. X is a prime number and x is between 50 and 80. This thing is mentioned over here, that x is lying between 50 and 80. Second property of x, we have x is a prime number. Now suppose I am talking about any number, say 74. Whether this belongs to this set or not, we are saying first thing we have, it lies between 50 and 80. It is satisfying this property that it lies between 50 and 80, but it is not satisfying the property that x is a prime number, so it is not the element of this set. Next we have two elements over here. One is h is equal to -1 and 1. So we are saying we can write it as these are the collection x. X is an integer and x square is equal to 1, or we are writing these are the roots of equation x square plus 1 is equal to x square minus 1 is equal to, not plus 1, it is x square minus 1 is equal to 0. So it is up to you that you can write it in this form, that h is equal to x, x belongs to z, x square minus 1 is equal to 0, or you can write it in this form, that roots of the equation x square minus 1 is equal to 0. Now the next we have listed over here some sets related to the number systems. So the first we have, it is the natural numbers. So natural numbers, we already know that these are the numbers used for the counting purpose, and these numbers we have listed over here. These are n is equal to the set, it is represented with capital N. These are the standard notations. This set, it is represented with capital N, and the numbers we have, it is 1, 2, 3, 4 and so on. Next is the set of whole numbers, it is represented with W. Whole number means it is all natural numbers plus this element 0 over here. These are the whole numbers. For details about all these numbers, you can refer to our previous videos, and particularly for the class 9th chapter 1, we have given the details of all these numbers over there. So next we have, it is the set of integers. Integer means all the positive and negative numbers and the 0. We are saying the 0, it is called the neutral element or neutral number. These are the natural numbers we have, and these are the negative numbers that we have. So all these numbers, positive natural numbers, then neutral element 0, and these negative numbers, they together form the set of integers, and the set of integers, it is denoted by z. The basic purpose of telling these sets, it is this notation you should know, that n is for natural number, w is for whole number, z is for integers. Next we are talking about positive integers. We are saying, if we are writing the integers, it is, we are writing the collection in this form, then it is minus 2, minus 1, 0, 1, 2, 3. We are saying this 0 is the neutral element. These are the positive integers. These are the negative integers. These are positive and these are negative integers. The positive integers, they are represented in this form, it is z plus, and this is basically equal to the set of natural numbers. Next we have negative integers. Negative integers, we have represented z negative. So this is the collection over here. It is minus 1, minus 2, minus 3, minus 4 and so on. This is the collection of negative integers. Next we have non-negative integers. Non-negative means those which are not negative. Those which are not negative, they are either positive or they are 0. So we are saying this is the set of all the integers which are positive or which is 0. So this collection is just equal to the set of whole numbers. We are saying non-negative integer means it is, we are talking about set of whole numbers. Similarly, non-positive integer means all negative integers plus this element 0 over here. These are called the non-positive integers. Next we have is the rational numbers. We know that rational numbers are all the numbers of the form p by q, where p and q, these are the integers. Integer will represent with z, and we are saying that q should not be equal to 0. Then this collection we are talking about over here, this is the set of integers. This is represented over here. We are saying it is q is equal to a by b. A and b belongs to I. I over here, it represents integers. Other notation for this is z over here. You can use z, you can use I over here. This is more common notation, or more standard notation is z for the integers. And we are saying b is not equal to 0. Further, sometimes we write it in this form, and HCF of a and b is 1, so that we are writing them in the simplest form. This thing is just for the sake of purpose that repetition is not allowed. If suppose we are writing 2 by 2 or we are writing 1, both these are representing the same integers. Both of these are representing the integer 1. Basically this rational number when we are talking about, so if we are saying it is 2 by 3 or we are writing it is 4 by 6, both these are representing the same rational number. So that is why this thing is mentioned over here, that HCF of A and B, that is equal to 1. That is, the number should be in the simplest form. Then that collection we are talking about, all these numbers will be different. That collection is called the set of rational numbers. Next thing we know is, when we are talking about the rational number, there are two kind of decimal representations. Either the decimal representation that will be terminating. This is not the case of we are talking about rational number, we are talking about any number is there, or we are talking about the decimal representations. So decimal representations may be terminating or they may be non-terminating. What we have is that if any number, if any value is given to us which has terminating decimal representation, then we are saying that is a rational number. Now for non-terminating case, further two cases arise. Either it is repeating or it is non-repeating. This first case, that it is non-terminating and repeating, this is also the part of the all these numbers, these are the rational numbers. And if any value is there whose decimal value is given to us which has representation which is neither terminating nor could be expressed as recurring decimal, it means neither it is repeating nor it is terminating, then those numbers, these are called the irrational numbers. The details I am again mentioning over here, the details of these you can refer to the chapter 1 of class 9. The next numbers or the next definition we have over here, it is the prime numbers. So a prime number is a number, a natural number we are talking about. It is important over here, we are talking only about the natural numbers when we are saying prime numbers. So it has exactly two factors. This word exactly is very important over here, that it should have exactly two factors, 1 and itself. So we are talking about the natural numbers over here. So the first natural number we have, it is 1. How many factors 1 has? It has only one factor 1. So it is not a prime number. Next number we have, it is 2. 2 has two factors 1 and 2. 3 has two factors 1 and 3. 4 has factors 1, 2 and 3. So we are saying 2 is a prime number, 3 is a prime number, but 4 is not a prime number. So this is the definition for the prime number, that it should have exactly two factors. So an important point to note over here is that 1 is not a prime number. Next is how to test a number. So let us suppose a number p is given to us and we want to check whether it is a prime number or not. So one method is that we have to check the divisibility of this p with all the numbers less than p. So in place of checking with all the numbers, it is better, or the method that we have, it is that we calculate the value of square root of p and we find all the prime numbers which are less than equal to square root of p. We list all the numbers, all the prime numbers which are less than equal to square root of p, and if this number p is not divisible by these numbers, then it is a prime number. So in place of checking with all the natural numbers, we are just checking with the prime numbers less than square root of p. So we are explaining this with an example over here. So we are saying, suppose p is equal to 193, this is the number given to us, and we have to check whether it is prime or not. So first step we have to write all the numbers. These x, we are saying it is prime, it is additional property over here. We are saying x is a prime number and x is lesser than 193. So the elements of this set x, it is 2, 3, 5, 7, 11 and 13. So these are the prime numbers less than, these are prime numbers less than square root of 193. Now we check the divisibility of 193 with only these numbers, and we can see that 193 is not divisible by 2, it is not divisible by 3, 5, 7, 11 and 13. So we are saying none of these divides 193. Hence 193 is a prime number. So this is one of the methods to check whether a given number is a prime number or not. The next definition we have is co-prime numbers. So two natural numbers are said to be co-prime if their HCF is 1. So we are saying, suppose we are talking about the number 15 and 16. If we look at the factors of these numbers, the factors of 15, they are 1, 3, 5 and 15. So 15 is not a prime number. When we look at this number 16, the factors are 1, 2, 4, 8, 16. 16 is not a prime number. But if we look at the HCF of 15 and 16, the answer we have 1. It means the common factor, these two numbers, it is equal to 1. Then these two numbers 15 and 16, these are said to be co-prime. So 15 and 16, these are co-prime numbers. Next is twin primes. So twin primes is a prime number that is either 2 less or 2 more than another prime. It is called a twin prime. So we are saying that twin prime is a prime that has a prime gap of 2. So example, these are given over here, that 3 and 5, the difference between these two, it is 2. 5 and 7, both these are prime and difference between these two is 2. If we are talking about 29 and 31, 31 minus 29, it is 2. So this pair is also a twin prime pair. Next is composite numbers. So composite numbers are non-prime natural numbers that have at least one factor apart from 1 and itself. So basically we are saying that composite numbers are those numbers which have more than 2 factors. So prime we are saying which have exactly 2 factors. Exactly 2 factors. Composite we are saying which have more than 2 factors. So if we look at this number 1, if we are talking about this number 1, it has only one factor 1. So it is neither prime nor composite. Next, if we are talking about, suppose the number 4, how many factors it has? Is a 1, 2 and 4. So it has more than 2 factors. It has more than 2 factors. So it is a composite number. Now the next definition we have, it is the real numbers. So the set of real number contains both the rational and irrational numbers. All the rational and irrational numbers, they are together called the real numbers, and this set is denoted by R. Now next we have some terms related to sets. So first term we have, it is the empty set. So a set containing no element at all is called an empty set. The other terms for this, it is the null set or void set. These may also be used over here. And the notation for the empty set we have, either we write it like phi, or this is the notation of set and we keep it empty over here, and we are saying these are the notations for the empty set. So we have a set which has at least one element, it is called the non-empty set. If it has no element, it is called empty set. If it has at least one element, it is called the empty set. So the examples that we have is, the first example we have, it is this set we are talking about. What this set means is, we are talking about X is the collection of all those natural numbers which lie between 2 and 3, and we know that no such number exists. We know that no such number exists. So we are saying this set is an empty set. Next is x. X is a number and x is not equal to x. This is not possible. All the numbers they are equal to themselves. So we are saying this set is also an empty set, that there is no element in this set which satisfies this property. Next we are saying x is a natural number which satisfy these two properties, that x is less than 5 and x is less than 7. This and is important over here. And means that it should satisfy both the properties. We want a number which is less than 5 and greater than 7, and there is no such number. So we are saying this set is an empty set. Next we are saying x is a real number and x square is equal to minus 1, and we know that there is no real number, there is no real number whose square is negative. It means this set is an empty set. Next is x such that x is rational. We want x to be rational number, and x square minus 2 is equal to 0. So if we solve this equation, the answer you will get it is x square is equal to 2. So this gives us x is equal to plus or minus square root of 2. And we know that this number square root of 2, it is irrational. It means there is no value of x which satisfies this equation. So the set we are talking about, it is an empty set, that there is no x for which x is rational and x square is equal to 2. X is a point common to two parallel lines. So we are saying the definition we have is that two parallel. Next definition we have, it is singleton set. So a set containing exactly one element is called a singleton set. So suppose I am talking about this 0 over here. So we are saying this set contains an element 0. It is important to note over here that this set when we are writing 0 and this set when we are writing it is empty set, these are two different things. Empty set means that it contains no element, but this set contains an element that is 0. This set has an element that is 0. So what we are saying is suppose I am writing this set as A and this set as B, then we have 0, this element we are talking about, this belongs to A, but 0 does not belong to B. So there is only one element in this set, and these kind of set, these are called the empty or singleton sets. Next is suppose a set has the element 15. Next we are saying x such that x is a natural number and x square is equal to 4. So if we solve this equation, we get x is equal to plus minus 2. But with this condition, because of the condition that x is a natural number, we are saying the answer we are remaining over here, it is x is equal to 2. It means this collection, this whole set, this is equal to 2. So we are saying this is the element 2, singleton element over here. So these kind of set, this is an example of a singleton set. Now in this same set we are talking about, if in place of x belongs to n, we are writing x belongs to z. In place of x belongs to n, we are writing it is x belongs to z. Then this set will have two elements, that is plus 2 and minus 2, and this is no longer a singleton set. The next definitions we have, it is finite and infinite sets. So first we are talking about the finite set. We have an empty set or a non-empty set in which the process of counting of elements surely comes to an end is called a finite set. So we are saying the number of distinct elements contained in a set A, which is denoted by n of A, and this value should be finite, that we can we are not using basically we can count. In place of count, we are saying that when we start counting the elements of that set, then that procedure comes to an end, then that set, it is called a finite set. So these are some examples given over here. This is the set A we are talking about. So how many elements it has? 1, 2, 3, 4, 5 and 6. So we are writing n of A is equal to 6. N of A is equal to 6 means we are talking about number of elements in set A, that is equal to 6. Second, we are talking about B. It is set of all letters in English alphabets. So how many letters we have? We know it is 26. So this set is also a finite set. Next, we are saying it is the set Z, C we are talking about. It is x is an integer and x square minus 36 is equal to 0. So we get the values of x, we have it is plus minus 6. So this set has 2 elements, so it is a finite set. Next is the set of all persons on earth is a finite set. It is important to see this example from the perspective that if we start counting the number of persons, it seems that we will get a very large number, but we will obtain a number. So this example, it explains that we are saying process of counting of elements surely comes to an end. So if we start counting the number of persons, it is 1, 2, 3, it may be 10 raised to the power 2, then 10 raised to the power 3, then 10 raised to the power 4, 10 raised to the power 5, 10 raised to the power 6. But somewhere we will find a last number when we are counting all the persons, howsoever large it is, but we will find a last number over here, and we are saying that this collection, it is a finite set. Next is set of all animals on the earth is a finite set. Similarly, we are saying if we start counting the animals, we are saying it is 1, 2, 3, so on. We may get a large number, say 10 is per 6, say 10 is per 7. Some number is over there. If we start counting those animals, some number will be there where the counting will end. So we are saying the number of the set of animals on the earth, it contains finite number of elements. It may be very large number over here, but it is a finite number. It is a finite number, and we are saying that this collection, the set of all animals on the earth, is a finite set. Next we have is infinite sets. So the set of all points on the arc of a circle, they are from an infinite set. So suppose we are talking about a circle is there, and we want to write the set of all points on the arc of a circle. We consider an arc of this circle. This portion, suppose we are talking about this portion we are talking about, and we have to write the collection of all the points over here. So there are basically infinite points. We cannot count these points, and this set, it is the set of all points on the arc of the circle. This is an infinite set. Similarly, the set of all points on a line segment. Suppose this is a line segment A, B we are saying, and we have to write the collection of all the points on a line segment. We are saying this is the plane. This is XY plane we are talking about. Similarly, this is the XY plane we are talking about, and we want to write the collection of all points over here. So we cannot write all these, or we cannot count all these points over here. So this forms an infinite set. Similarly, the set of all circles passing through a given point. We are saying this point is given to us, and we are drawing the circles passing through this point. So these are the circles we are talking about. These may be the circles. These circles may be like this. These circles may be like this. So we cannot count the number of circles passing through a given point, or we are saying if we start counting the number of circles, we are not saying we cannot count. If we are saying if we start counting the number of circles, then suppose I have drawn 10 circles, then I can draw the 11th circle. Next, if suppose I have drawn 10 raised to the power 10 circles, after that I can draw 10 raised to the power 10 plus 1th circle. So we can keep on drawing the circles in this way. So we are saying that it is not going, if we start counting the number of circles, this counting is not going to end, and we are saying that this collection, it is a infinite collection. So this set, the set of all circle passing through a given point, it is an infinite set. Next is the set of all straight lines parallel to the x-axis. So we are saying, suppose these are our axis, this is x-axis, this is y-axis. We have drawn the straight lines over here, and we start counting these lines. Suppose we are saying this is the first line, this is the second, this is the third, this is the fourth. Then the counting is not stopped over here. We can say we can draw another line over here, this will be the fifth line. After this we can draw another line, this will be the sixth line. In this way the counting, this counting will not stop at some point. So we are saying the number of the elements in this set, it is infinite. So it is set of all straight lines parallel to x-axis, it is an infinite set. Next is the set of all positive integral multiples of 5. So positive integral multiples of 5 means 5, then 2 into 5, then 3 into 5, then 4 into 5. This will keep on going like this. So this is also an infinite set that we cannot count, that if we start counting the number of elements in this set, then our counting will not end. Similarly, the set of natural numbers, integers, rational numbers, real numbers, irrational numbers, these are all infinite sets. And it is mentioned over here that it is not always possible to describe an infinite set in the roster form. So, and as an example, we have shown over here that if we are talking about the set of real numbers, it is not possible to describe these numbers in the roster form, because we cannot find any pattern in these numbers to describe them. This is more clear to you with this example. We are saying the set of all positive integral multiples of 5. We have shown this set over here, that it is first element is 5, then it is 2 into 5, that is equal to 10. Next element we have 3 into 5, that is equal to 15, and we can say it is so on up to infinite number of elements are there. So there is a pattern over here that it is 2 into 5, then 3 into 5, then 4 into 5, and so on. But when we are talking about the set of real numbers, we do not have any form or any particular pattern in which we can write these numbers. So that is why we are saying that it is not always possible to describe the infinite sets in the roster form. Now the next definition we have, it is equal sets. So two non-empty sets A and B are said to be equal. First we are talking about two non-empty sets are there, and they are said to be equal if they have exactly the same elements. It means the number of elements is the same, and all the elements are same. We have two conditions. First, the number of elements we count, they are same, and all the elements, they are same. Then the two sets, they are said to be equal, and we write A is equal to B. If any of these condition is not satisfied, then we are saying that those two sets, they are unequal sets. An important thing to note over here is that the ordering of the elements and the repetition of elements, it is not to be considered when we are talking about the equality of sets. It means if we are writing the set 1, 2, 3, we are writing the set 2, 1, 3, or we are writing the set 3, 1, 2. The number of elements, they are 3. elements we have, it is 1 over here, 1 over here, 1 over here, 2 over here, 2 over here, 2 over here, 3, 3 and 3. So number of elements are same and the elements they are same. So all these three sets, these are equal to each other. Similarly, we are writing, if we are talking about the set 1, 2, 3 and we are talking about the set 1, 1, 2, 2, 3, then we already know that the repetition of elements in a set has no meaning. When we are talking about this set, how many elements it has? We are talking about, suppose the set A is equal to 1, 1, 2, 2, 3. So the number of elements of A, that is equal to 3. When we are talking about the set B, that is equal to 1, 2, 3. The number of elements of this set B, it is equal to 3. Why we are saying so? 1 is repeated twice. So this is basically, we are writing it as 1. This is 2. So repetition is immaterial, is meaningless when we are talking about the set. So the number of elements in this set A, that is equal to the number of elements in this set B, and the elements they have, they are also same. So we are saying both these sets, these are equal to each other. Next we have is A is a set, the letters in the word follow, and B is the set of letters in the word wolf. So is A is equal to B. So when we are writing this set A, we are saying the elements we have, it is F, O, L and W. When we are writing the set B, the elements we have, it is W, O, L and F. Number of elements in both these sets, it is number of elements in A, that is equal to number of elements in B, that is equal to 4, is W, then it is O, then it is F, and last element we have, it is L. So elements, they are same, number of elements, they are equal. So we are saying both these sets, A, the set of letters in the word follow, and B, the set of letters in the word wolf, both these sets, these are equal to each other. Next is phi. This set 0 and 0 are all different. This phi means it is the empty set, it has no element. Second, we are talking about this set, it has an element 0. 0 is element of this set. You are saying 0 is element of this set. So when we are writing this, so we are saying 0 is an element of this set. So this is not a, this thing we are talking about, when we are writing 0 only without any brackets, is not a set. So these three things, that writing phi, that is empty set, writing in 0 in bracket, it means it is a set that contains the element 0. And third thing we have, when we are writing 0 only, it is not a set. So 0 is not a set. Next we have is, two sets are given to us. One is the set A, it is x such that x is a natural number and x square minus 9 is equal to 0. So we are saying x square is equal to 9, x is equal to plus minus 9. When we combine both these equations, the answer we get, x is equal to 9. Second, we are talking about x square is minus 9 is equal to 0 again is there. So we are saying x is equal to plus minus 9. X is belongs to z. It means x is an, in this case x is a natural number. Over here x is an integer. So the elements of this set, so the elements of this set will be plus 9 and minus 9 because x is an integer. The elements of this set, it is only 9 because x is a natural number. Number of elements in this set, it is 1. Number of element in this set, it is 2. So we are saying both these sets, these are not equal to each other. Next we have is equivalent sets. So two finite sets A and B are said to be equivalent if the number of elements in A and number of elements in B, they are equal. So it is important to note over here that equal sets are always equivalent, but equivalent sets need not be equal. So we are talking about an example over here. The set A contains the element 1, 3, 5. So number of elements in A is equal to 3. Number of elements in B is equal to 3. So from these two we are getting number of elements in A is equal to number of elements in B. So we are saying both these sets, these are equivalent sets. But in A we have an element 1 over here which is not present in B. So we are saying both these sets, they are not equal to each other. So their elements, they are not same. Next we have to show that this set 0 containing element 0 and this set 5 are not equivalent sets. So when we are talking about this set A that is equal to this, so the number of elements in A that is equal to 1. The element we have, it is the element in A, it is 0. 0 is an element of A. But when we are talking about this set 5, how many elements it has? It has no elements. So the number of elements in B that is equal to 0. So we are saying both these sets, these are not equivalent sets. Next we have which of the following are examples of the null set? So it is set of odd natural numbers divisible by 2. We have to write the set of all odd natural numbers divisible by 2. So we are saying there is no odd natural number which is divisible by 2, otherwise it will become an even number. So this set is a empty set or null set. Next is set of even prime numbers. So this set contains an element that is 2. 2 is an even number. It is also a prime number. So this set is not an empty set. Next is the set X. So X is a natural number and these are the values given to us. It is important to note over here that this is equal to sign over here. So this set, it contains an element 2. So this set is not equal to empty set. Next is X is a natural number and it is given that 2x plus 3 is equal to 4. So when we solve this equation, we get x is equal to minus 1 by 2, which is not a natural number, which does not belong to the set of natural number. So we are saying that there is no number x, there is no number x which satisfies this condition. So this set is equal to empty set. We are saying that we cannot find a number which satisfies this condition. So this set is an empty set. Next is x square plus 1 is equal to 0. It means x square equal to minus 1. And we know that there is no natural number x whose square is minus 1. It means this set is equal to empty set. Next is x plus 3 is less than equal to 3. We are talking about x plus 3 is less than equal to 3. It means x is less than equal to 0 and x is a whole number. So it means x is equal to 0. So this is equal to the set which is 0. 0 is a number over here. And we are saying that this set is not equal to the empty set 5 because it contains an element that is 0. So there is difference between 5 and this set 0 over here. Next we have which of the following are examples of the singleton set. So the first we have is x square is equal to 4. So x is equal to plus minus 2. And it is given that x belongs to z. So the set we have, it is equal to plus 2 and minus 2. So this is not a singleton set. Next we have is x plus 5 is equal to 0, so we get x is equal to minus 5. So this set, and x belongs to integers, so this set is minus 5, so this is a singleton set. Next we have is mod of x is equal to 1. This definition of mod you will study in your next classes, that it is the positive value of any number. We can just, for the sake of simplicity, I am defining it in this way, that it is just the positive part or the positive value of that number. Exact definition we are going to study in our next chapter. So we are saying all those z such that mod of x is equal to 1. So if we are saying if x is equal to 1, then mod of x is equal to 1. If x is equal to minus 1, even then mod of x is equal to 1. We are saying whatever value of x is there, we take the mod, will make it to the positive, make it to the positive number. So how many elements this set has? It has two elements, 1 and minus 1. So this is not a singleton set. Next is x is an even prime number. If we are talking about even prime numbers, so 2 is only the even prime number. So this is an singleton set because it contains only one element. So if we are talking about this set 0, this is also a singleton set. But when we are talking about this empty set or phi, these are not the singleton sets. Next is, which of the following are pair of equal sets? So first is A, that is equal to the set of letters in the word alloy. So if I write them in this form, it is A, comma L, comma O, comma Y. So how many elements it has? Number of elements in A, it is 4. When we are talking about this set B, the elements we have, it is L, O, Y, A. Number of elements in B we have, it is 4. First thing is both these sets, these are equivalent sets. Next we have to check the corresponding elements, A, then L, then O, and then Y. The corresponding elements are also equal. So we are saying both these sets, these are equal to each other. Next is the set C, that is equal to plus minus 1, and second set we are talking about, it is x square is equal to 1, x is equal to plus minus 1, x is belongs to z, so it means this set is equal to 1 and minus 1. So the corresponding elements of both these sets, these are equal. So we are saying both these sets, these are equal to each other. Next is, which of the following are pairs of equivalent sets? So equivalent means number of elements we have to count. So number of elements in A, that is equal to 3. Number of elements in B, that is equal to 3. So both these sets A and B, these are equivalent sets. Number of elements in E, that is equal to 5, and number of elements in F, that is equal to 5. So both these sets, these are equivalent sets. Next is, state whether the given set is finite or infinite. So we are saying A is the set of all triangles in a plane, so it is an infinite set. Next is the set of all leaves on a tree. So we are saying if we start counting the number of leaves, 1, 2, 3, so we will find a last leaf over there, and we can count these numbers of leaves. We can find a number for the last leaf that we will have. So we are saying this set, it is a finite set. Next is C, the set of all positive integers greater than 500. So we are writing it is 501, 502, and so on. So this is an infinite set. There are infinite number of elements in this set. Next is x belongs to R, 0 is less than x is less than 1. So if we are talking about these numbers, so we are saying this set is also an infinite set. Why? Suppose I am writing the number, say I am talking only about the rational numbers. So I can write all the numbers 1 by 2, then 1 by 3, then 1 by 4, then 1 by 5, and so on. These are I'm not writing all these numbers. I am saying these all numbers, these are part of this set. And how many numbers we have? There are infinite such numbers. There are other numbers also. The other numbers will be, then it is 2 by 3, then it is 2 by 5, then it is 2 by 7, like this. Other numbers are there. But we are saying if we are talking about only these numbers, these are infinite in number. So this set, it is an infinite set. That is the number of elements in this set we cannot count. Next is E is equal to x belongs to z and x is less than 1. So all the integers less than 1, they are, it is 0, minus 1, minus 2, minus 3, and so on. So we are saying this set is also an infinite set. Number of elements over here, there are infinite elements, that we cannot count the number of elements in this set. So this set is an infinite set. Next is rewrite the following statements using set notation. So first is A is an element of the set A. So we write it like A belongs to A. B is not an element of A. It means B does not belong to the set A. A is an empty set. It means A is equal to 5. B is a non-empty set. B is not equal to 5. Next is number of elements in a set A is 6. If we have to write this, it is number of elements in a set A is 6. Last is 0 is a whole number but not a natural number. It means we are talking about that 0 belongs to the set of whole numbers and 0 is not a natural number. 0 is not, does not belong to the set of natural numbers.